If the people here have read this, I'll now switch it off somewhere. We continue the theme of proteomics and genomics by moving on to genomics, specifically microarrays, and our first speaker is Brien from the University of South Australia. Thank you, Chris.
Thanks, Terry. So, the outline of my talk for today is I'll firstly introduce some terminology and notation that I'm going to use in the talk. Then I'll look at a quite simple example of an observational study with technical replication. Move on to look at what you might do when you've got a split plot experiment that you then want to take material into the process using microarrays, and then finally there'll be a summary. So firstly I'm going to use randomization diagrams and tiers. Tiers is a term that I introduced in an 83 paper. Randomization diagrams are something that Rosemary and I describe in our red paper at the JRSS in 2006. So I'll illustrate these concepts using the fairly simple design, a randomized complete block design, which I would describe as two-tiered. So you've got T treatments that you want to apply to BT units using this design, and what I've got there is a randomization diagram that's got two panels, the panel on the right-hand side and the panel on the left. And a panel is for a set of objects, so I'm saying that I've got one set of objects which are my T treatments and another set of objects are my BT units, and I want to assign the treatments to the units. And in each panel there's a list of factors in a tier, and their numbers of levels and their nesting relationships. So you can see we've got two factors in this right-hand panel, blocks and runs. They have B and T levels, and runs is nested within blocks. So a tier is just a set of factors, nothing more complicated than that. In this experiment, it's two-tiered. It involves two sets of factors, one set being just the factor treatments and the other set being the factor blocks and runs. But not just any old set, a set of factors with the same status in the randomization, because we've got that these set are the unrandomized factors and these are the randomized factors. And indeed, most textbook designs are two-tiered, and in fact you don't really need this word if that was all you're going to deal with. We could just stick with talking about treatment and unit factors or whatever, or something similar. But in practice, there are experiments that are multi-tiered, and so we need to think about more than two sets. This diagram shows, if you like to think about these things, the experimental unit and restrictions placed on randomization. Experimental units run in a block, and we've restricted the randomization to the runs within blocks. So that's randomization diagrams and tiers. Mixed model notation. Terms in the mixed model correspond to what in the JRSS paper we call generalized factors. Generalized factors are just factors formed from original factors. So if you have a factor A with little a levels and a factor B with little b levels, we think of A wedge or meet B as the factor formed from the combinations of those two factors, and it will have a little a times little b levels altogether. So we mean that joint factor, if you like. I'm going to use symbolic model form derived from the symbolism talked about by Patterson in a paper in '97, where you have the fixed terms on the left, a straight line, and then to the right of that straight line, the random terms. So my example is a two-factor factorial structure on the left for my fixed terms, getting out of hand here, fixed terms, and I've got two terms on the right that are my random terms, and this corresponds to a mixed model which looks something like this. So you've got an X matrix and a theta for each of your fixed terms, and a Z matrix and a U for each of your random terms. And so the thetas are your fixed parameters and the U's are your random parameters, and you've got some usual sorts of assumptions that you make about the U's. Their expectation is 0, and the variance of them is sigma squared j, I should say, depending on which component you're dealing with. I could leave the last one out here and replace that with a unit error term E. That's quite commonly done in packages. I'm not going to do that because I'm not going to specifically identify them, but that will be an equivalent model. So, but from here on, when I have a mixed model, it's going to look like this. I'm not going to give the matrix expression for it. Then I want to be assessing a design for an experiment, and I'm going to describe a general method that uses tiers and pseudo factors actually quite a lot, in which we get a decomposition or ANOVA table that shows the confounding for the design. We formulate a mixed model, and we'll have an actual model and often a model of convenience that we have for doing the fitting because of the limitations of the fitting process. And then we derive the variance of treatment means based on expected mean squares, treatment mean differences. Here, I'm only going to deal with what Terry referred to 3 weeks ago as array design, that is the assignment of material, or what he called analytes, to the chips. This is the bad news for Terry. I'm not going to talk about anything that happens in the lab phase. I understand that's very important, but I'm not going to consider it in this talk. So the answer to his question before lunch isn't in this talk, I'm afraid. I'm going to illustrate the method, as I said, for a simple example with material from an observational study, and then I'm going to apply it to a more complicated case of material from an experiment. So, an observational study, suppose we've got tissue from a naturally diseased organism and a normal organism. We get a sample of mRNA from each, and we have 8 arrays spotted with fractions, which of course correspond to technical reps, from both samples using a quadruple dye swap design as described by Kathleen Kerr in 2003 in biometrics. So it's this kind of design, and what you can see is you've got 8 fractions from the diseased sample and 8 fractions from the normal sample. And in considering a randomization diagram from that, what we've got is we've got 2 dyes by 8 array combinations that we want to apply our conditions and the fractions to. So we've got, this is 2 tiers. We've got the conditions and the 8 fractions in each condition, giving 16 fractions altogether that we want to apply to the 16 array die combinations. Thinking about the fractions, well, firstly I will assume that we've just got 8 sets of indistinguishable arrays. There's no batching or anything like that, which you might want to take into account and so give you a different structure for the array dies, but we're assuming that's not the case. You can consider randomizing the 16 fractions that you've got, the 8 within each conditions, and I guess there's a question whether that's necessary. Maybe you don't need to do randomization at this stage. Maybe nature's done the randomization for you, or maybe there is something systematic and you do, or maybe it's not even possible. Maybe the way fractions are collected, they just come out of a machine one after the other and there's no way of taking 8 fractions and randomizing them. But even if that's the case, what you have to do is somehow organise the experiment so you get 1 fraction from the diseased and 1 fraction from the normal on each of the arrays. And the way to record that is to use a pseudo factor to identify pairs to randomise or perhaps to assign, or that just end up on a particular array. So and this will identify one, as I say, one fraction from the diseased and 1 from the normal that ends up on each array. And so we set up that 8-level pseudo factor, which I've called F1, F because it's a fraction pseudo factor, and 1 because it's the first one. And then you want to assign the conditions to the die array combinations, and the die swap design tells us how to do that. And so in fact we're going to apply conditions to these array die combinations according to the design that we had up here. My notation here is that I'm applying it to these combinations. I haven't got just any old way of applying to those combinations. I've got a design that tells me how to do that, and in fact it's an orthogonal design, so I've got a perp in the middle of that to indicate that that's the case. So that details the randomization that you might employ in such an experiment. And if you apply that, you might end up with a randomization that looks like this. Well, you've got 4 arrays that have disease with the first dye, perhaps a red dye, and normal with the green. There's 4 such arrays, and then there's 4 around the other way, and there's mixtures of individuals that occur as a result of randomizing if you can do that. As I said, if you can't randomize, these might just be a random, these might be the same number. You know, this might be individual 2 from disease with individual 2 from normal, for example, if you can't randomize them independently. Okay, that's my randomization diagram that tells me how I might have randomized this. How am I what's in the decomposition table? It shows me what's confounded with what. That arises out of this experiment. Well, I'm going to work it out using Hasse diagrams, and to get Hasse diagrams what you've got to do is do one for each of the two panels that I've got there, and I'll start with the array die panel. And so what I do is take all the combinations of the factors that are valid given the nesting, and in this case including the universe factor as always. In these sorts of diagrams I've got the factor arrays, the factor dies and their combinations, and the numbers next to them are the numbers of levels of each of those factors. I also, unlike what, well, sort of a little bit differently to what Ching Shui did yesterday, I've also got the sources that correspond to these factors, and we've got a 1 degree of freedom for the grand mean, which of course we never put in the analysis of variance table, but I've got a 7 degree of freedom main effect for A, a 1 degree of freedom main effect for dies, and we've got 7 degrees of freedom for the arrays dies interaction. So I'm using the hash here to indicate that that's an interaction between A and D. Same thing for the fractions tier or the fractions objects. Here are the set of factors that are all combinations that are valid giving the nesting. Here we don't have fractions on its own because it's nested within conditions. And the numbers of levels are given, and then I can add the sources, the conditions main effect with 1 degree of freedom and 14 degrees of freedom for fractions within conditions. And now I want to use this Hasse diagram with these sources to form a decomposition or analysis of variance table which summarises the properties. First, I'll write down all those sources that I've got over here in the arrays dies diagram. So I've just listed them down, and then I want to add to that the sources that I've got in the fractions diagram. Well, there's a slight problem in that the fraction variability, or that term fractions within conditions, is split over all three array die sources. So I can't just, well, I can write it in there, but I need a way to explicitly say which parts are randomised with which. And this is where the pseudo factors come in. I could ignore them and just leave the fractions out of the analysis, or if I want to keep them in there and retain it as a source of variation, then I need to use pseudo factors to do that. And so that's what I've done, and in fact we've got the pseudo factor F1 that we set up before that tells us the contrast amongst the fractions that are confounded with arrays, and we'd have to set up a second pseudo factor that tells us the contrast between the fractions that is confounded with dies. That would be, of course, a 2-level pseudo factor. And then we've got down the bottom here the remainder of the fractions within conditions. There's supposed to be a horizontal perp there that I've obviously lost the character. So that you can take that to mean that's the bit that's left over. That's orthogonal to the two pseudo factors F1 and F2. So that's my analysis. It tells me I've got fraction variability everywhere, and I've got conditions confounded because of the design with the array die interaction. But of course these pseudo factors, they're not real. They're just ways of partitioning up the total fractions within conditions. The source of variability is fractions, and so we would replace those pseudo factors with the fractions within conditions term to indicate that they are in fact all from the same source of variability, fraction variability. A mixed model, well, to get the mixed model, all I've got to do is take all the generalised factors that I've got in the diagrams and decide whether they're fixed or random, and then that will give me a mixed model that I can use for my experiment. In this case, I'm saying the conditions and dies are fixed, and then arrays and arrays, dies combinations, and the fractions within conditions are all random terms. So that would be my mixed model in this case. So this is just that analysis of variance table. Again, you can get the expected mean squares using standard rules. Haven't got time to go through this, but in fact there's a paper in the American Statistician, I think it's by Law, published in '95 that tells you how to do this. The good thing is you don't need to worry about the pseudo factors in getting the expected mean squares. So in fact this is the Hasse diagram with the components. We've got a component for each of our random terms here, and we've got a quadratic function of the expectation, in fact a quadratic form divided by degrees of freedom for the fixed term, and we work out that the contributions to the sources in terms of these components are given by the expressions on the right-hand sides of the dots. Similarly, for conditions, you've got two components, a fixed sort of quadratic component and a variance component, and these are the contributions. And so then we can add those to our analysis of variance table, putting in the one from the arrays dies diagram. We just copy the various contributions in, and of course the sigma squared AD has got to go to both. And then I add to these contributions against the terms that they are. So the fractions within C contribution, sigma squared CF, will go against the three fractions within C terms, and you'll end up with this set of expected mean squares. So that's the expected mean squares. This is the sort of traditional analysis of variance table we put up. It's very similar. You get exactly the same partition of the total sum of squares. What's different is that you've got just an error term that's undifferentiated error source, whereas in the analysis here you can see there's an error source for stuff that comes from the hybridization sort of technique and stuff that comes from the preparation or the fraction part. And this table doesn't show the confounding, but it's not really that big a difference. You wouldn't be going to all this trouble just to get the table on the left versus the table on the right. It's really, I think, in the next example that things get interesting. The one thing here is that these two components are obviously inseparable, and if you in fact put that model that I gave you up the top here into a mixed model package, it would fail to converge because of that aliasing, and you need to drop one. And so this would be a mixed model of convenience, not the actual mixed model, but one that you can do the fitting with. To get the variance of the difference between condition means, you just take it as twice the expected mean square for conditions, ignoring the Q function, and divide by the replication of the condition mean, so that's easy to get once you've got the expected mean squares. So that's my simple example. The more complicated example is a split plot experiment. This example comes out of a paper published by Millikan last year in Statistical Applications for Genetics and Molecular Biology, and they had started off with a split plot experiment, and then they wanted to process material from it using microarray technology. This is a two-phase experiment of the type introduced by McIntyre back in '55. The first part's a split plot experiment on grasses, in which a randomized complete block with 6 blocks is used to assign the two-level factor precipitation to main plots, and each main plot is split into 2 subplots to which a two-level factor temp is randomized. So our randomization, you've got 24 subplots, 6 blocks within which you've got 2 main plots, within which you've got 2 subplots. You've got 4 treatments, 2 precipitations that are assigned to the main plots, and 2 temperatures that are assigned to the subplots. So even though there's 2 factors randomized there, and you might think there's 2 randomizations happening, we regard this as a single randomization of treatments to subplots because it can be done with 1 permutation of the subplot factors. So that's one randomization, and it leads to an analysis of variance table that looks like this. So you've got a term for the blocks, a term for main plots, a term for subplots, precipitation confounded with main plots, temperature and its interaction confounded with subplots. The usual sort of thing. Here's the set of designs, that were, I saw some of your eyes go up. This is the set of designs that Millikan investigated for this experiment. So it's not as difficult as it looks. There's 3 designs. This first one has the same T, so the same temperature but different pressure assigned to an array. So each of these arrows represents an array. So this array is going to get both temperature 1s, but it's going to have precipitation 1 and precipitation 2 on it. So it's going to be from different main plots. And in fact, there's 3 blocks that are like that. 1, 3, and 5 are exactly the same. The only difference is the material came from different blocks. The other 3 blocks, 2, 4, and 6, are the die swap of that. So that's one possibility. The next possibility is that you use different T and different P. So you can see the combination here is it's got both the 1, 1 for precipitation and temperature, whereas it's 2, 2 for temperature and precipitation here. And the final one has different T but the same P. So in fact it has the material out of 1 main plot on it. And then again, in every case, 1, 3 and 5 versus 2, 4 and 6 is a die swap. I'm going to just look at the analysis of this one, just one. And the randomisation, actually Millikan and et al. Don't actually discuss how you might what randomisation might be appropriate here. But we've got the sort of setup we had before. We've got array dice combination, 12 arrays in this case, and we've got our subplots that we want to randomise. And you can't just think about taking the main plots and somehow randomising to arrays, because what you've got is the precipitation randomised to main plots. And if you just forgot about precipitation and assigned main plots, you would end up with your precipitation horribly non-orthogonal. So we have to look at our main plots and take into account what precipitation happened. We're going to assign the blocks to arrays, as we saw on the previous slide. But in fact, to keep main plots in the analysis, what we want to do is come up with construct a pseudo-factor, M1, that's going to tell us which precipitation was on which main plot. And in fact, M1 will be just equal to the P factor, the precipitation factor, because it'll have a 1 for main plots that got level 1 of precipitation and a 2 for the main plot that got level 2 of precipitation. But it's different in that we're considering it as a pseudo-factor of M, not telling us what precipitations directly were given. You do the same thing for T, derive a pseudo-factor that tells us which subplots got T1 and T2. And again, I've got a little problem with symbols. This should be a diamond. This says that the precipitation determines that and the temperature determines that. And then once I've got that, I can apply the precipitation and main plot factor in combination with the treatment and subplot factor to the array die combinations using the plan B that was on the previous slide, although there's not going to be any thought of there are particular array blocks. So it's essentially what you're doing now is taking the two pseudo factors with the original factors. And I mean, again, you could do what Millikan and co did and ignore the pseudo factors, but what will happen is you won't have sources for main plots and subplots included in the analysis. This sort of randomisation up here is called randomised inclusive randomisation. It involves 3 tiers, and this is one of the 6 sorts of randomisation that Rosemary and I described in our joint paper in 2006, the BMB 2006. Mixed model, pretty straightforward. What you do is you take all the generalised factors and take them from each of the panels and decide which of them are fixed and which are random. So what I've done here is put the PT and the PT combinations as fixed. I've also taken dies out of here as random. The 3 terms, or the 3 generalised factors that come out of subplots are random, as are arrays and array die combinations as before. So that's a mixed model. That in fact has no block treatment or inter-tier interactions. Turns out that Millikan et al. Decided that they would have interactions of die with the 2 treatment factors, and we can do that. We can modify our model, include all those interactions, and this is a shorthand that says take all 3 factor factorial effects for PT and D. So not a problem. Okay, we want to get the analysis of variance table. Well, the sources for array dies is just what we saw before. You've got these 3 sources that come out of the Hasse diagram if you want to do it that way. And then we want to take the subplots within main plots and the main plots within blocks. But the trouble is they are actually split between arrays and die sources. So again, we need to introduce pseudo factors. And if we do that, we get this analysis. It's too complex. I don't have time to explain it at the moment, particularly since I've got now less than 5 minutes. But what you'll see is that subplots with 6 degrees of freedom is confounded with arrays, and the remaining 6 degrees of freedom with the interaction, 1 degree of freedom for main plots with die, and the remaining 5 with the interaction. So the last thing we want to do is get the treatment sources. Turns out that the PT interaction is confounded up here with the array sources, and so are the other 2 factor interactions. They're up here. And that the precipitation and temperature are confounded down here with this interaction, which will be different from the other designs, but that's the full analysis. This is the analysis on the right. Here is the analysis of variance given in Millikan et al. Exactly the same partition, so they got the right sum of squares. The labels differ. They use what I call artificial grouping factors like block type and array pairs, not pseudo factors. And you can see there are things like block type and array pairs coming out in the analysis. Their labels don't show the confounding, and hence the sources of variation are obscured. For example, you can see that the PT interaction has subplot variability and array variability because it's confounded with each of those sources, but their expected mean squares are correct, and that you can see from the expected mean squares what sources of variation are contributing. It's just that in this table you can see it, it's intuitive from this table, I think. So their tables, though, are unrelated to the terms in the model. These aren't the terms that they have in the model. It's pretty much similar to mine, and I sort of feel that the rationale for their decomposition is unclear. So you could work out the expected mean squares using those standard rules that were published in that American statistician paper, and you'll get this set of expected mean squares. Millikan et al. Use an ad hoc procedure for each design that takes 4 journal pages for each design to work out the expected mean squares, which I think is a bit long. And so I think a general procedure like this is an improvement, I hope. Mixed model of convenience. Well, here you'll see that the sigma squared AD and sigma squared BS always occur together, so you can't separate them. You can only estimate one. If you put the model that I had in before into a package, it's going to blow up, not converge because of that aliasing. You need to drop one to get a fit. So this is my model of convenience. I've dropped the BMS term, and it is equivalent to the Millikan model. To get the variance of mean differences, you can use the expected mean squares. So, for example, the variance of the difference between 2 precipitation means is the expected mean square for precipitations minus the Q divided by its replication and times 2. So that's pretty straightforward. So in summary, the microarray designs for observational material 2-tiered, those for experimental are multi-tiered, and randomisation of further stages along the lines that Terry's talking about will need more tiers. I think the use of tiers and randomisation diagrams leads you to explicit consideration of the randomisation for array designs, which is perhaps often overlooked. It's a general method for synthesising the decomposition table, mixed model and variance of mean differences. Using pseudo factors retains all the sources and avoids the artificial grouping factors for real sources of variation, so that you get the terms in the table and the model are directly related. And there's a link to an address where I've got material, where there's a lot of material on multi-tiered experiments, although not this material. I only got that together in the last couple of weeks.
Thank you. Questions or comments? Sit here till we get one.
It's pretty much tied up with this microarray situation of having a pair of 2 dies. Will it extend to?
Oh, certainly. I mean, if you had a multi-die situation, that just affects the kind of design you're going to employ in getting the material onto the chip. But it's certain there's no problem.
What about the loop designs have been used in this context in that situation?
Yeah,
Why not treat one as a particular reference?
You can work out what that's amenable to this. I mean, I have got I had a lot more examples, but it was clear I didn't have time to go through them all. But no, loop design you could work out analysis in this kind of way for that as well. Oh, Roger.
Just a comment. The analysis is often rather nastier because what you tend to be given are log intensity ratios, and for that you need to collapse some of the within die swap aspects, and I think it gets a lot nastier, the estimation. But I think having at least a concept of where the variation is coming from is absolutely crucial to analyse this. And I think as microarray experiments do get rather larger than just looking at half a dozen sorts of material on replicate chips, this kind of technology is going to be crucial to make sure we get the right analysis.
Yeah, I mean, in this paper, the Millikan paper, they're suggesting that microarray technology is getting cheaper, and you're going to get more cases where you take a whole experiment, which wasn't the case, a field experiment or something like that, and apply it. And I've heard Andrew Mead say the same thing and others. So it seems like the material collection part of it's going to get more complicated, and so you might have to think about this a bit more carefully. Well,
Okay, let's thank Chris once more.